Welcome to our 7th episode on our series on mathematical language and symbols. In this presentation, we will be talking about basics on relations. But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos. Before we jump to the definition of a relation, let us discuss first a prerequisite concept. This is very important for us to fully understand what relation mean in mathematics. This prerequisite concept is on the Cartesian product of two sets. The Cartesian product of two sets, say A and B, denoted by A cross B, this is a symbol for a cross product of two sets, is the set of all ordered pairs AB such that A is an element of the first set A and B is an element of the second set B. This means that the elements of a cross product are ordered pairs. Sometimes we term an ordered pair A point. Let us provide an example. Suppose we are given two sets. The first set contains the numbers 2, 3, and 4, and the second set B contains the number 4 and 5. If we are to identify the elements of A cross B, it would be the following points. We are going to pair all the elements of the first given set to the elements of the second set. And if we do that, we can identify 1, 2, 3, 4, 5, 6 different ordered pairs from the given two sets. It is important to note that if we are identifying the cross product of two sets, the order is an important thing. For example, for each ordered pair, the first number must come from the first set and not the other way around. Let's have another example. We are given two different sets C and D. We can see here that the elements of C are four numbers. They are 1, 3, 6, 7. And then the elements of the second set D, it contains three different numbers. If we are going to identify C cross D, then we have to pair the four numbers in C to all the numbers in set D. If we do that, we can identify 12 different ordered pairs or points. We can pair 1 with 2, that's our first ordered pair. Also, we can pair 1 to 4, that's our second pair. If we do that, we can complete the 12 ordered pairs. If we want to check if we already exhausted all the possible ordered pairs that we can identify from two given sets, we simply have to multiply the cardinality of the two sets and then check if that's the number of ordered pairs that we have identified. For example, the cardinality of set C is 4. The cardinality of set D is 3. If we multiply that, we have 12. That 12 represents the number of ordered pairs that we can identify from two given sets. If we go back to our first example, the cardinality of A is 3. The cardinality of B is 2. If we multiply them, it's 6. So there should be 6 ordered pairs in our cross product. Let's now proceed to the definition of a relation. A relation simply is just a subset of A cross B, and this subset is more completely termed as a binary relation from A to B. From our earlier videos, we explained what we mean by a subset. This is a subset from a given set if all of its elements are elements of the given set. Here are notations that we use for a relation. The ordered pair xy in A cross B, x is related to y by this symbol, and this is the way we write if and only if the ordered pair xy is an element of this set. Another terminology, we call it the domain of the relation R. That is the set comprising all the first element of the ordered pairs included in the relation. The set B, that's the second set we are working on, is called the co-domain. If we are going to collect the second number in each ordered pair, that's B, in all the ordered pairs that are included in a relation, that set is called the range. Let's have an example for it. Suppose we are given two sets A and B. We can see here the elements. These are the same sets that are given in our first slide. Our cross product is the set containing 6 ordered pairs. If we're going to take any subset of this set, that is already considered a relation. We have 3 different possible relations here, and our goal is to identify if that is a relation from A to B. Based on the sets that are given here, we have relation 1. It's the set containing two ordered pairs 2, 4, and 3, 5. If this is to be a relation from A to B, then this set must be a subset of the cross product. So we check that the 2 points are also elements of the cross product. Yes, the 2 points here are elements of the cross product. Therefore, this is a relation from A to B. The second relation contains 2 points also. However, we can identify that 1 point here is not an element of our cross product. That is the reason why this set is not a relation from A to B. 5, 4 is not found in our cross product. This is our third set. It's the null set. Is the null set a subset of A cross B? We also mentioned this in our previous video that the null set is an automatic subset of any given set. In fact, this is called the empty relation. So yes, this is a relation from A to B. Another example, we are given 2 sets, but this time the elements are names. We can see here that set A contains names of 3 people, Alex, Barbie, and John. And then the second set, set B, contains 3 names, Anna, Joseph, and Claire. Let us define a relation from the 2 given sets. And we're going to name it C. Since a relation is just a set, then we can name it with a capital letter. We define the relation C as the set of all ordered pairs X, Y, such that X is related to Y if X and Y are different sex. Of course, it's given here that Alex, John, and Joseph are guys, while the rest are girls. And this is the definition of our set, that 2 people, that's an ordered pair, is an element of our relation if they have different sex. Let us list all the elements of relation C. We have Alex, Anna, Alex, Claire, Barbie, Joseph, John, Anna, and John, Claire. We have to check that the condition for the relation is satisfied. That is, for each ordered pair, the 2 people here have different sex. What is the reason why we do not consider this as the value of the relation C? We can see that we have an element, we have an ordered pair, Joseph, Barbie, and this is a violation because Joseph comes from the second set. Another one, this is still not the elements of relation C because of a violation. We have Joseph and Anna for the same reason. Another example, we have 2 sets with different elements. Our first set contains 5 elements: flour, strawberry, egg, rice, and bugnay. For those who do not know what bugnay is, this is a fruit. Our second set, it contains 3. Spanish bread is just treated as a single element. We know that because it's not separated by a comma. So Spanish bread is a single element of set B. Another element is wine, and another is jam. Let us define a relation. We are going to name it P, relation P, such that X is related to Y, or the ordered pair XY is an element of our relation P if the first element of that ordered pair X is an ingredient to make the second number in that ordered pair Y. Let us list all the elements of relation P. The answer is this set. Our first ordered pair, that's flour and Spanish bread. Spanish bread is a bread, so you need flour to make Spanish bread. Jam. Can you make a jam out of a strawberry? Yes, so strawberry is an ingredient in making a jam. Strawberry is also an ingredient in making a wine. That's why we have a strawberry wine. Egg is an ingredient to make a Spanish bread. Rice is an ingredient to make a wine. The product is called rice wine. And then bugnay can be used to make a wine. The result is a bugnay wine. But we can never add an ordered pair like flour and jam. Can you make a jam out of flour? Or egg jam? Is there such thing as an egg jam? I don't think so. Another example, our sets here are again numbers, and the definition of our relation is called L. The ordered pair XY is an element of our relation L if the first number in that ordered pair X is less than the second number in that the same ordered pair Y. So this is the relation. This is the condition of whether an ordered pair from the cross product of these 2 sets here is an element of the relation L. If it is an ordered pair from the cross product but it does not satisfy this condition, then that would make the relation wrong. based from this definition. Let us again list all the elements of relation L. It should be 1, 4, 1, 5, 2, 4, 2, 5, and 4, 5. We should see to it that the first number in each ordered pair is less than the second number. So 1 is less than 4, 1 is less than 5, 2 is less than 4, 2 is less than 5, and 4 is less than 5. The domain for this particular example, what do we mean by domain again? This is the set containing all the first number of each ordered pair. So the first number in our first ordered pair is 1, 1 still for the second ordered pair, and then 2 for the third ordered pair, still 2 for the fourth ordered pair, and then we have 4 for the last ordered pair. If we are going to collect those first numbers, then we would have the set containing 1, 2. So although 1 is repeatedly used, if we're going to write our domain, then we should write the repeated numbers here once. The codomain is the set B. We need simply to copy the second set, but for the range, we are collecting the second numbers for each ordered pair. So we have 4, 5, 4, 5, 5. So it ranges only from 4 and 5. That's the range of our relation. Another example, but this time we are given a single set because we are going to define a relation from the given set to itself. So we are actually working on two sets. It's just that the two sets are the same. We call it a relation on A. The definition is that ordered pair is included in our relation M if X is greater than Y, meaning the first number in that ordered pair is greater than the second number of the same ordered pair. Let us list all the elements. We have 2, 1, 4, 1, 4, 2, 5, 1, 5, 2, and 5, 4. We see that the first numbers here are actually greater than their pairs. Relations can also be illustrated using other means. We call them arrow diagrams and tables. So aside from writing our relations using set notation, we can use arrow diagrams and tables. Let us use the same examples and write them in arrow diagram and tables. This is from our example number 2. To use an arrow diagram, we're going to represent the first set like this. So normally it's an oval or a circle, and then we write the elements of that set here, and then we do the same for the second set. And then for all the elements of our relation, for example, this first ordered pair, Alex and Anna, we're going to draw an arrow, a one-sided arrow from Alex to Anna. So we have Alex to Anna. And then for our second ordered pair, still from Alex, but it's going to another element of our second set, that is Claire. We do the same for the rest of the ordered pairs. And if we are done, this is the arrow diagram equivalent of relation C. If we want to use tables, we should do this way. We're going to write the elements of the first set in our first row, and then their pairs in the second row. So for example, the first pair here is Alex and Anna, so we should see Alex and Anna in our table. We can draw it horizontally or vertically. We do the same for the relation defined in example number 3. These are the elements of relation P. If we convert this into an arrow diagram, we write this way. If you want to check, you may pause the video and check. Tables, we do the same. From example 4, let us draw the equivalent arrow diagram and table. So these are the elements of relation L, and then we put arrows depending on what are the elements of our relation. That is 1 and 4, 1, 5, 2, 4, 2, 5, and 4, 5. Using tables, we do it this way. In all our examples so far, we've been working on finite sets, but a relation can also be defined between infinite sets. For example, the first set that we are talking about is the set of real numbers. The second set that we are going to consider is still the set of real numbers, so that the cross product is called R cross R. R cross R is still a set containing ordered pairs, and we want to define our relation from this cross product. So we're going to take a subset of R cross R. Since there are infinitely many points, we are working with infinite sets, so the elements of R cross R should be also infinite. Listing the elements of a relation for this case is different if we're going to make use of our roster method. If you observe from our previous examples with our finite sets, we were just simply listing the elements of our relation by way of the roster method. This time, since we are working with infinite sets, we're going to write our sets using the set builder method. Also, appropriate for relations defined from infinite sets is to make use of the Cartesian coordinate plane. So we are going to plot all the points in our set. Remember, a relation is composed of several points. For each point, we're going to plot it in our Cartesian plane. I hope you are familiar with your Cartesian plane. A Cartesian plane is created by two perpendicular lines. These lines are more commonly termed as your axis. The horizontal line is called the x-axis and the vertical line is called the y-axis. Their intersection is the origin, and for any given point, we can plot it in our Cartesian plane. So that in each point or ordered pair, the first number that we see there corresponds to a number in our x-axis, and the second number there corresponds to a number in our y-axis. Here is an example of a relation defined from infinite sets. Specifically, we are defining it from the set of real numbers to itself. That means from the set of real numbers to the set of real numbers. And we are going to call our example here relation F. And the definition is, an ordered pair is an element of F if it satisfies this condition. What is this condition? The square of the first number in an ordered pair plus the square of the second number in the same ordered pair, the sum must be equal to 1. All the points that satisfy this equation here should be an element of F. That's why sometimes we say that we can write a relation using an equation, because instead of listing the points, the ordered pairs, we simply write the equation that defines that particular relation. So how should we write F in set builder method? We write F is the set of all ordered pairs xy such that, here is the condition, such that x squared plus y squared is equal to 1. Of course, x and y should be elements of the sets we are working from. If we're going to convert this in terms of a graph, it would look like this. If we are going to graph all the points such that the sum of the squares of each of them is equal to 1 should look like this. If we're going to do that for many points, a figure is formed, and that figure is a circle. So that when we see a graph, we do not actually interpret this as just a line that we draw, but a locus of points, many points, such that we cannot actually see the gap between each points and then just see them as a continuous curve. Let's provide another example of a relation defined from infinite sets. Here is the definition of the relation. We call it H. This is the set of all ordered pairs xy, and the definition of this relation is that the cube of the first number minus the cube of the second number in the same ordered pair must be equal to 1. If we put that in graph, it looks this way. Another example, and another one. There you have it. Relations and some examples. I will see you in the next video for a discussion on a specific type or kind of a relation called functions.